Okay, so welcome back. Last time we talked about the bosonic and fermionic harmonic oscillators, and we developed these two. We developed the mathematics for these two harmonic oscillators, right? Now we're going to use these two harmonic oscillators to essentially get to what is called a supersymmetric harmonic oscillator. And well, as you can pretty much guess, it is the supersymmetric harmonic oscillator is actually a linear combination of the bosonic and fermionic harmonic oscillators, and which then essentially implies that the Hamiltonian for the supersymmetric harmonic oscillator would actually be a linear sum of your bosonic oscillators Hamiltonian and the fermionic oscillators Hamiltonian. We are going to start by making an assumption, in fact, and that assumption is essentially that these two bosonic and fermionic oscillators do not interact. So there is no interaction between bosonic harmonic oscillator and fermionic harmonic oscillators, which mathematically would just mean that these two commute with each other, correct? We already know that the fermionic harmonic oscillator or the fermionic system is it is described or by these B and B Dagger operators. These are the creation and the annihilation operators for a fermionic system, and we also know that for a bosonic, the operators are A and A Dagger. Right now, what this no interaction term, this statement essentially means is that these commute with each other, right? Okay, great. So now coming back to the supersymmetric Hamiltonian, if you recall, the Hamiltonian for the bosonic system was simply A dagger A plus 1/2, and then you have this plus, and the fermionic system was simply B dagger B plus 1/2, and there was a negative 1/2 over here, right? And then if you simplify this, you just get A dagger A plus B dagger B, and so this is the Hamiltonian for your supersymmetric harmonic oscillator. Beautiful. Now we can we can talk about the Fock space for the supersymmetric harmonic oscillator, like we have talked about these Fock space for bosonic and harmonic oscillators as well. The Fock space for the supersymmetric harmonic oscillator is labeled by N, B, and NF, right? So this would be the state. Now the point to note over here is that NB can take any values from 0, 1, 2 up to infinity, and then that essentially comes from the definition of a bosonic system, and the NF can take values 0 and 1, right? Only these two values are allowed for NF, and that again essentially comes from the definition of a fermionic system, right? Okay, good. So now let's move further and define something that is called a supercharge. CHARGE, right? Okay, so well, a supercharge is actually it is a conserved charge. Conserved under what? The charge is conserved under Noether's theorem, right? and this conserved charge is of a supersymmetry transformation, right? So oh well, what you can say is it is actually a generator of supersymmetry transformations, right? So it is a generator of supersymmetry transformations, and you denote this supercharge by the letter Q, capital Q, and it is essentially an operator which will transform bosons under supercharge to fermions, right? And vice versa, right? So another thing to note over here, because of this fact, which we'll look at in a moment mathematically, but because this fact is true, the supercharge operator, it changes a particle essentially with spin 1/2 to a particle with spin 1 or 0. The supercharge itself is it is a spinner, right? It is a spinner which carries half unit spin, right? Okay, so well, if you go into a more detail of supercharges, they're also called Grassmann variables, and mathematically speaking, they are then the generators of the exterior algebra of anti-commuting numbers, right? And these numbers are the Grassmann numbers, and if you want to we talked about Grassmann numbers in the previous lecture, right? We did not go into a detailed analysis of Grassmann numbers, but we mentioned what Grassmann numbers are. And so the another thing to note over here is that the supercharge, it is described by what is called a super Poincare algebra, right? Okay, now we'll define the let's define the supercharge Q. It is defined as A B dagger, right? So now let's look at what happens when you have this operator Q and it acts on a state that is essentially NB, and NF is equal to 0, right? So it is a bosonic state and not a fermionic state. So this thing is actually a bosonic state. Now let's see what this action does. So we'll replace Q by A B dagger, and we have the state NB NF equals 0, and let's the operator B dagger will operate on NF, and you're left with A square root 0 plus 1, which is essentially 1, and you'll have NB, and NF will be now equal to 1, right? Now the final thing that you have to do is now operate with A on this state. This square root of 1 is just a constant and it's 1, so you're only left with A on this state, and that would be you'd have square root. Now note that this will act on this NB because it's a bosonic operator, and you'll be left with NB is times the state, which is NB minus 1, and NF equals to 1. So this state is now a fermionic state. And so we have we have proved that what this supercharge does, it takes your bosonic state and it transforms it into a fermionic state. So we can write that down over here as another point, that you have Q and it acts on a bosonic state, and it gives you square root NB times the fermionic state. Right. So now we have talked about this supercharge. You can also look at the you could call it an inverse or the dagger of supercharge, because if you are applying this operator to a bosonic state and going into the fermionic state, there should be an operator as well that if you apply it to a fermionic state and it takes you to a bosonic state, right? And you can check that if you simply take Q and Q dagger and take a bosonic state, and you would have over here, then you'd have Q dagger on a fermionic state, and so this is 1, and therefore a Q dagger on a fermionic state would give you the bosonic state, right? So then Q dagger is simply defined as, well, what was Q? It was simply A, B dagger. So the dagger of this thing itself then is simply B, A dagger. Now, it would be a nice task for you to compute the action of Q dagger on NB, NF equals to 0, and Q dagger on NB, NF equals to 1, right? And then you can also check what Q does to NB and NF equals to 1. So you can try this yourself and see what the result is. We'll move on to the Hamiltonian, right? And the Hamiltonian, if you recall, was for the supersymmetric oscillator. We wrote it as A dagger A plus B dagger B. Now you can check the commutation of the Hamiltonian with the supercharge, and it's a very simple task, because all you have to do is write the Hamiltonian as A dagger A plus B dagger B, and then your supercharge as A B dagger. And now what you have to do is just open this commutator. This commutator is using the properties of a commutator. You can write this commutator as A dagger A plus B dagger, plus it would be plus A B dagger, right? And then you have plus B dagger B and A B dagger, right? And you can solve this, and you will see that what you get, the whole thing essentially vanishes, right? And so we conclude that the Hamiltonian and supercharge commute with each other. And you can also check the same thing for Hamiltonian and the dagger of supercharge. It will also commute with each other. You can also then write down the anti-commutator for supercharge and the dagger of supercharge, and you can compute this by Q dagger plus Q dagger Q, and all you have to do now is just put the values A B dagger, and you would have over here B A dagger plus B A dagger and A, B dagger, and then you can apply it to a state, and you can see that this essentially gives you back A dagger A plus B dagger B, which if you look at here, it is simply the Hamiltonian for the supersymmetric oscillator. And so what we conclude that the anti-commutator of the supercharge and its inverse is essentially the supersymmetric Hamiltonian itself, right? And these let me highlight these things. Okay, so what you have over here, this thing, and this thing is what essentially defines the supersymmetric algebra, right? So let me write over here. So this is what defines the SUSY algebra, right? Okay. Nice. So we have established that the Hamiltonian commutes with the supercharge. So if you have, let's say you have Hamiltonian that acts on some state psi, and let's say that the state psi is a bosonic state. Well, let's first write down this equation. This is the eigenvalue, or also the Schrodinger equation. H psi equals E psi, and because the Hamiltonian commutes with the supercharge, this basically means that if I had Q on the state psi, this would also be the eigenstate of the Hamiltonian, right? So you can then if you have this thing, Hamiltonian on Q and state psi is equal to EQ on state psi. And now let me first, okay, now let's define state psi. Let's say that this state psi was actually a bosonic state. So then we already know that Q on psi is a fermionic state, right? So this thing would have if this thing, let's say if this thing psi, it had some energy E, then this thing Q on psi would also have the same energy E, right? So and this is simply because again the Hamiltonian commutes with the supercharge, right? And because it does so, Q on state psi is the eigenstate of the Hamiltonian with the same eigenvalue E, right? And therefore what that essentially means physically is that if a bosonic state had some energy E, then its corresponding fermionic state would also carry the same energy E, right? Okay, so well, this is pretty much it for a supersymmetric harmonic oscillator, and we'll talk in more detail about some other things, such as we'll see how to solve the Hamiltonian systems in a later video as well. Let's conclude this by listing some of the properties for this SUSY harmonic oscillator, and these properties are, well, if you write down the Hamiltonian, which was A dagger A plus B dagger B, and well, you can define these operators A dagger A as some number operator N for bosons and the number operator F for fermions. So this would actually give you the number of the bosons and number of fermions. And if you take their sum, So it will always be greater than or at least equal to 0, right? So what this essentially means is that the energy of the supersymmetric harmonic oscillator or a supersymmetric system would always be greater than or equal to 0. And because of this fact that this is true, one may find supersymmetry as it reveals the beauty of this theory of supersymmetry, because one might be tempted to believe that it's true, and the reason for that is because if you have theories that give you negative energies, the theories are basically unstable, or the system is unstable, if it carries negative energies, and we see that this would not give you a negative energy, but it would always be positive. And so a supersymmetric system tends to be a stable system, and one is tempted to believe believe that the theory is true indeed, right? Okay, so we talked about this in a much more detail in the first lecture on this series, where we talked about the motivation for supersymmetry, right? Okay, so this is one of the properties, and the other property of the SUSY system is that if you have a ground state, what would be the ground state? It would be NB equals 0 and NF equals 0. So this is the ground. This is the ground state of the harmonic oscillator. What happens if I take my operator supercharge Q and I act it on this state, NB equals 0 and NF equals 0? Well, if you recall, Q was simply Q was defined as a B dagger. So a B dagger acting on this state would basically kill the ground state, and this would just give you 0, right? And so what that means is that the ground state is annihilated by the action of supercharge on the ground state, right? And the final or at least the third property is again that we already talked about this. The Hamiltonian is NB plus NF. So this essentially means that if I were to write down the ground state energy for NB equals 0 and NF equals 0, this energy is simply equal to 0. So the ground state energy of the supersymmetric harmonic oscillator is 0. Now in the next lecture, we'll hopefully talk about the spontaneous breaking of this supersymmetry. And what happens over there is that these last two properties that we have talked or listed over here, these will essentially change if the supersymmetry is spontaneously broken in your system, right? So let's conclude this video over here, and in the next one we'll hopefully talk about the spontaneous supersymmetry breaking in your system.